this is a general introduction to the binomial probability distribution because we were unable to have the class last Saturday, and so I'm introducing you to it. We'll take some examples in the class on Saturday to reinforce what I say. So, in the previous class, we looked at the general probability distribution for the discrete random variable, and we're still talking about discrete random variables, but we're looking at a special distribution called the binomial distribution. This distribution is unique because the trial that we're using has some characteristics that have to be satisfied for us to apply the binomial distribution. And so we're talking about a Bernoulli trial, and it has the following characteristics. The first is that we're looking for an experiment that has n identical trials. And this means that every time we conduct a round of this experiment, we're doing the same thing. So if we were to flip a coin 10 times, 100 times, 1,000 times, that would be referred to as identical trials, because the act of flipping the coin is the same thing that you're doing 100 times, 10 times, how many times you do it. In addition to that, the experiment must have only 2 outcomes. Or the outcome should be of such that we could reduce it to 2 outcomes. For instance, a multiple choice exam has each question will have maybe 4 or 5 options, but there are only 2 outcomes there that are important, whether the answer is correct or incorrect. So in that case, we can reduce the number of outcomes to 2, and we refer to those outcomes as success and failure. Now, these are not used in the literal term that we use success and failure. These refer to what we expect to find, what we're looking for when we conduct the experiment. So for instance, if we're flipping a coin, we're looking to see how many times out of 10 times the coin will land on the head. Every time the coin lands on the head, that will be referred to as success. Every time it lands on the tail, that will be referred to as failure. So success is not necessarily something good, failure is not necessarily something bad. For instance, if we're in the quality control department of a company and we're looking to see how many defective items come off the production line, every time we find a defective item, that will be referred to as a success. And if we find one that's not defective, that will be referred to as a failure. Now, importantly as well, the trials have to be independent. This means that every round of this experiment, the outcome is not affected by the outcome we got on a previous round. So for instance, if we're flipping the coin, if we get a head this time, the next time we flip the coin, it does not affect the probability that we get a head or a tail on the next trial. So the trials have to be independent. The probability of getting an outcome when you do it the first time should not affect the probability of you getting another outcome on another trial. And finally, the probability of success we call P, and the probability of failure we call Q. Now, because the trials are independent, the probabilities of success and failure will be constant throughout the experiment. And so, for instance, flipping a coin, probability of getting a head will remain as 0.5 for every round of the experiment. Likewise, probability of getting a tail will not change. And so once our experiment fulfills these criteria, then we can apply the binomial formula and find the probability that we're looking for. Now, there are 2 ways of finding binomial probabilities. We can use the binomial table. There's a very long table, and so we will not be using the table for this course. We will apply the binomial formula, which looks like this. Probability of x is equal to n factorial divided by n minus x factorial times x factorial times p to the x and q to the n minus x. Now, some of these terms will look new to you. The first of which being this exclamation sign, which is what we refer to as a factorial. And what this means is that we're multiplying in by all of the whole numbers lower than itself. So for instance, if we have 5 factorial, that is equal to 5 times 4 times 3 times 2 times 1. Now, fortunately for us, with the introduction of scientific calculators, we don't have to do this manually. Your calculators will have the factorial function. On most calculators, it's just above the 4. So if you're looking for 5 factorial, you enter 5, second function 4. It will give you the answer that you need. See if you can find it on your calculator. If you can't, just come to me before the class on Saturday and I can help you find that. So, the factorial. Now, the first part of this formula is what we call the combination. And so, for instance, if I were to, on your final exam, if I put 5 questions there and I say, answer 3 out of the 5 questions, I want to know how many possible combinations of 3 I can get from 5 questions. I can apply the combinations formula and I can find the outcome, the answer. Also for things like the lottery, you have 31 numbers, you have to pick 6 numbers. You want to know how many possible combinations of 6 you can get from 31 numbers. You can apply this formula and find the answer. Now, what do the other terms in this formula mean? The n refers to the number of trials. X refers to the number of successes that you're looking for. And P is the probability of success. Q, probability of failure. Now, because this is also a probability distribution, the sum of the probabilities have to be equal to 1. So P plus Q is going to be equal to 1, which means that if you give me P, Q is going to be equal to 1 minus Q. And likewise, if you give me Q, then P is going to be equal to 1 minus Q. The point is that when you sum the two, you have to get to 1. We're still with probability distributions. So this formula is applied again when our experiment satisfies the characteristics of the Bernoulli experiment or the Bernoulli trial. And so there's one application for binomial distribution in business, in sociology, right across the social sciences, right across the spectrum actually. And so we're working with, we are going to take an example or two to reinforce how we use this formula. Now, a lot of questions are going to be given to you in worded format, which means that you have to be able to read the question, extract all the things that you need for the formula. So, right, so I'm going to use an example from worksheet 4 to highlight, to reinforce how we apply the binomial formula. So, there's a question on the worksheet that says, it's talking about MRI, it's a medical procedure. They have to scan your brain, and so they have to put you into this machine, but it's a very enclosed machine, and so a lot of people are claustrophobic like myself. And so sometimes when people come to do an MRI, they're claustrophobic, they can't do it while they're awake, so they have to sedate them before they can do the procedure. And so on a particular day, 5 patients show up to do an MRI. We want to know what's the probability that exactly 2 of those 5 patients will have to be sedated. From previous information, we know that 20% of the patients coming to do MRIs are claustrophobic and will have to be sedated before they do the procedure. So, can we apply the binomial formula to this question? So we have 5 patients coming to do an MRI. That's 5 times we have to do the same procedure, and so that's basically 5 identical trials. And so we have our n, which is equal to 5. We want to know what's the probability that exactly 2 of those 5 patients will have to be sedated. They're claustrophobic, and so we're basically looking for 2 successes, because for us success is when a patient has to be sedated. From previous information, we know that 20% of the patients are claustrophobic, and so the probability that a patient is claustrophobic is 0.2 And so our probability of success is 0.2, which means that our probability of failure is 1 minus 0.2, which is equal to 0.8. So we have everything that we need for the binomial formula. And so now we can go ahead and put that into the formula. So we're looking for the probability that x is equal to 2. Remember I told you that for these probability questions, you have to head them up correctly. You have to word your responses correctly. So we're looking for 2 successes. We're looking for the probability that x is equal to 2. So this is equal to n factorial, n is 5, that's 5 factorial divided by n minus x, that's 5 minus 2. Notice that the factorial is outside the bracket, so you have to minus the values in the bracket and then apply the factorial, times x factorial, which is 2, times p, which is 0.2, to the x, which is 2, times q, which is 0.8, to the power of 5 minus 2. Now, if you go to your calculator and enter 5 factorial, the answer you'll get there is 120. And so then you have 5 minus 2 factorial, that's 3 factorial. And if you put that into your calculator, you will get 6 times 2 factorial, which will give you 2, times 0.2 square, which works out to 0.04, times 0.8, 5 minus 2 is 3, so we're looking at 0.8 cubed, and that is 0.512. Now, so another thing to remember as well is you have to divide here before you multiply across. A lot of students make the mistake of multiplying across and then dividing. Then you work out the combination part of the formula first, and then you multiply across. So this is 120 divided by 12, which is 10, times 0.04 times 0.512, which works out to be 0.2048. And so probability that x is equal to 2 is equal to 0.2048, which means that there's about 20.5% chance that exactly 2 of these 5 patients will need to be sedated. And so remember, in applying the binomial formula, I recommend that you extract these values. You read the questions, you extract these values and write them somewhere before you put them into your formula, because when you're working with numbers, mistakes are very likely, and so to minimize the chance of error, when you extract these, you read out the question, ensure you're using the right value in the right place, and then you apply your formula. So, if we wanted to know the probability that none of these patients will have to be sedated, all 5 of them will be fine, nobody will be claustrophobic, we can again apply our formula. Now, for the same problem, when you're looking for the probability of a different number of successes, everything else about the question remains the same. The only thing that changes is your x value. So it means that this x is now equal to 0 because we're looking for the probability that. So, as I was saying, the only thing that will change in the formula is the value of x, because the only thing we're changing is the number of successes we're looking for. So x is now equal to 0. So wherever we have x, we change the value to 0. So we now have 5 factorial divided by 5 minus 0 factorial times 0 factorial. Now there's something special about 0 factorial. It is always equal to 1. So if you see 0 factorial, that is equal to 1. Times 0.2 to the 0 power times 0.8 to the power of 5 minus 0. So 5 factorial is still equal to 120 divided by 5 minus 0, that's the same thing as 5 factorial. So we also have 120 times 0 factorial, which we just said is equal to 1, times 0.2 to the 0 power. Now anything raised to 0 power is equal to 1, times 0.8 to the 5th power, which is 32768. So this will cancel out. We're left with 1 times 1 times 0.3276. So the probability that x is equal to 0 is equal to 0.3276. So you can do further practice with this question if you just manipulate the number of successes. If you want to know the probability that all 5 of these patients will need to be sedated, change x to 5 and work the formula. If you want to know the probability that 4 out of the 5 persons will have to be sedated, change x to 4 and rework the formula. Now, worksheet 4 is available for you in the library. Go get a copy. There are lots of questions on the binomial experiment, and you can practice now. On Saturday in class, we will take some more examples because we won't always be looking for the probability that x is equal to something. For instance, we want to know the probability that at least one patient will be sedated. At most, one patient will be sedated. At least 2 patients. We want to know how we can manipulate this to find those probabilities. We started talking about it when we looked at general probabilities, but as it applies to the binomial experiment, we also would need to apply some of that. So that's the sort of variation we'll be looking at in the class on Saturday. And so if you have questions, you can ask me on Saturday or you can comment on the video or something. But I need you to look at this before you come to class on Saturday.